So, we've all seen this absolute explosion of AI-generated art, right? It's everywhere. And some of it is just stunning. But have you ever really stopped to wonder what's going on inside the machine's head? I mean, how does a computer actually learn to be creative? Well, that's exactly what we're going to get into. We're going to pull back the curtain and look at the three big ideas, the three different minds, if you will, that let an AI create these amazing, original images from basically nothing. So yeah, what's the thinking behind the art? Our journey starts with the first massive breakthrough in this space. And honestly, the best way to understand it isn't as code, but as this epic, high-stakes game between a master art forger and a brilliant detective. This whole setup is called a generative adversarial network, or GAN for short, and it's made of two neural networks that are literally competing against each other. On one side, you have the generator. Think of it as our art forger. Its only job is to create images that are so convincing they look like the real deal. Then on the other side, we have the discriminator, our detective. Its whole mission is to be the world's best art critic and spot the forger's fakes every single time. So how do they actually get better? Well, it's this brilliant feedback loop. The forger makes an image. The detective takes a look and makes a call, real or fake. If the detective spots the fake, it gets a little reward, and the forger learns what not to do next time. But if the forger actually fools the detective, it gets the reward, and now the detective is forced to get smarter. You repeat this adversarial game millions and millions of times, and this constant pressure forces both of them to become incredibly good at their jobs. The end goal here is this perfect state of balance, something called a Nash equilibrium. This is the point where the forger gets so good, so masterful, that the detective is basically just guessing. It's only right about 50% of the time, no better than a coin flip. And at that point, our AI artist has pretty much perfected its craft. It's making images that are, for all intents and purposes, indistinguishable from reality. But there's a huge catch. This high-stakes game has a really critical vulnerability. See, all that intense competition, it can backfire, and backfire in a big way. The weakness is called mode collapse. So here's the problem. The forger, the generator, it kind of gets lazy. It realizes, hey, I don't have to master every single style of art. I just need to find one or two cheap tricks that can fool this detective every time. Imagine you train it on a huge data set of every dog breed out there. Instead of learning how to draw beagles and poodles and German shepherds, it discovers that for whatever reason, making pictures of golden retrievers is super easy and it works really well. So it just starts cranking out endless golden retrievers. All diversity just vanishes, and the model completely fails to learn the full picture you wanted it to. Right, so that instability meant we needed a new way of thinking. And that brings us to the second mind of AI creation, a much more organized, less chaotic method known as the variational autoencoder, or VAE. Now, instead of a competition, a VA is more like a master librarian. It takes in every single image in its library, and rather than just storing them, it creates this perfectly organized map, what we call a latent space. Every image gets compressed down into a single coordinate, a single location on this map, and then it learns how to do the exact reverse. You pick any coordinate on that map, and the VA decodes it back into the image that's supposed to live there. But this approach has a really big trade-off. VAEs are incredibly stable to train. You don't have that adversarial game, so there's no mode collapse. You get this beautiful, continuous map of ideas where you can literally travel between cat and dog and watch the image smoothly transform. The catch? Because the VAE is forced to average things out to make this nice, neat map, its final creations often end up looking a little blurry, a little less sharp than what a top-tier GAN can produce. So you get a great map, but the art itself is just a little less vibrant. Okay, so we've got the sharp but unstable forger and the stable but blurry mapmaker. This whole situation set the stage for the third, and right now, the most powerful approach, an elegant breakthrough that powers pretty much all of the state-of-the-art models you see today, diffusion. The core idea behind diffusion is just pure genius, seriously. Think about a sculpture. A sculptor starts with a random block of marble, right? Well, in our case, the AI starts with a screen of pure random noise. First, it learns the process of destruction. It takes a perfect, clean image and just systematically adds noise to it, step by step, until it's nothing but static. Then, and this is the magic part, it trains a network to learn the exact reverse of that process. It learns how to start with pure noise and little by little chisel away all that static to reveal a masterpiece underneath. Now, the first version of this technique, it worked directly on the pixels of an image. And the results were amazing, but it was painfully slow. I mean, trying to sculpt a huge, high-resolution photo from noise, pixel by agonizing pixel, took a ridiculous amount of computer power. It was just totally impractical for almost anyone. And this is where the truly brilliant move happened. Researchers thought, wait a minute, what if we combine the best of both worlds? What if we use a VAE, our map maker, to first squish a giant photo down into a tiny compressed summary, a little latent coordinate, and then we can run that super powerful diffusion process on that tiny summary instead of the whole massive image. And that idea, that's latent diffusion. It's the core concept behind models like stable diffusion that you hear about all the time. And the impact of this one idea? It was staggering. Just by working in that tiny, compressed, latent space, the whole process became about 50 times more efficient. This was it. This was the key that finally unlocked high-quality, state-of-the-art AI image generation for everybody, letting these incredible models run on normal, consumer-grade computers. So, there you have it. That's the journey. We went from the adversarial forger to the organized mapmaker, and finally to the powerful sculptor. Now let's put it all together and really compare these three minds of AI creation side by side. This table really breaks it all down, doesn't it? You can see the trade-offs clearly. GANs, they give you super sharp images, and they're incredibly fast, but training them can be a total nightmare. VAEs are stable and give you that fantastic, interpretable map of ideas, but the pictures can be a bit blurry. And diffusion? Well, it gives you absolutely state-of-the-art quality, and it's stable to train, but it's by far the slowest to actually create an image. The main takeaway here is that each of these has its own place in the modern generative toolkit. But this quest for the perfect AI artist is far from over. Diffusion is still pretty slow. Models still struggle to understand really complex prompts, like getting the right number of fingers on a hand. Getting fine-grained control is still a huge challenge. And of course, the massive area of ongoing research is just making sure these powerful models are used responsibly and safely. So we've seen machines learn to forge, to map, and to sculpt. They can now generate images that are often completely indistinguishable from reality. And that leaves us with one final, really fascinating question. Now that the challenge of generating reality is largely solved, what becomes the next grand challenge for artificial creativity?